Hi. So let's carry on with our discussion about the speed of sound. And in this session, we will do a very fast recap of what we've done so far, and then go on to do a brief recap of the Mach number, which we've already seen. But since the Mach number has to do with the speed of sound, we will start paying a little more attention to it, and we will pay some attention to the characteristics of subsonic and supersonic flows. In other words, flows that are slower than the speed of sound and flows that are faster than the speed of sound. We will also discuss the concept of characteristics and so on and so forth. So let's get right ahead. And so as we've discussed, sound waves are a consequence of compressibility, right? Right. So in other words, the all-important divergence of u being equal to 0 is no longer valid, right? However, one important thing to be kept in mind is that in a given medium characterized by a given background density, pressure, and temperature, it represents a characteristic speed at which small disturbances propagate. And this is a very important adjective, small disturbances, right? So it is compressibility, all right, but compressibility with regard to small disturbances. Okay. Put another way, it's a characteristic speed at which small disturbances propagate in a given medium. Now, you have to, if you recall the derivation of sound speed that we did during the previous session, we had assumed u naught to be equal to 0, and u naught was the background speed, if you remember, right? However, the speed of perturbations, which was what was this is the perturbation speed, right? Perturbations, this was not equal to 0, obviously not, right? So I'm talking, or I clap or something, that causes density and pressure perturbations, and u1 is the speed of these small perturbations, and that's not equal to 0. And it is these small perturbations which always propagate at the speed of sound. This is to be kept in mind. It has nothing to do with the background speed. Okay, although the derivation assumes u naught equal to 0, this need not be the case. We can put u naught not equal to 0. We can generalize and get an equivalent derivation for u naught not equal to 0. And so what will happen when u naught is not equal to 0? What will happen is that when the background speed u naught is taken to be not equal to 0, you can go through the entire derivation, okay? And what will happen is that instead of the dispersion relation omega square equals c sub s squared k squared, which happened when u naught is equal to 0, we will have omega squared minus some sort of v squared k squared equals cs squared. That's what will happen. In other words, there will be some kind of a Doppler shift. This is very much like a Doppler shift. Okay, so when u naught is not equal to 0, but it's some finite value v. But the thing to keep in mind is that the speed of sound s is the characteristic speed, all that is fine, speed at which small disturbances propagate, and this is very important, with respect to the background. And this is a very important statement. Okay. So, you see the small disturbances, they are propagating at the speed of sound, okay? And that speed is always c sub s with respect to the background. But what if the background itself is moving? In other words, what if the background speed u naught is not 0? Well, one simple thing to do is just climb into the frame of the background flow, and then you will find that the characteristic speed at which these small disturbances propagate is simply c sub s, because you are in the frame of the background gas, and therefore, now u naught is equal to 0 as far as you are concerned. But what about the fellow who is standing in the lab frame? What about the Eulerian frame? Then what will happen is the person in the Eulerian frame will observe that the small pressure and density disturbances which characterize the sound waves are not propagating at the sound of speed. They are propagating at the speed of sound. Sorry, I keep saying sound of speed, speed of sound. They are propagating at the speed of sound plus or minus the background flow. In other words, for u naught not equal to 0, as far as a lab observer is concerned, the small disturbances propagate at Cs plus or minus V, where V is the background speed. And this is very important. Okay, it's only so c sub s, I mean the speed at which these small disturbances propagate is indeed c sub s with respect to the background. If the speed of the background is equal to 0, well then no problem. I mean it's c sub s as far as the observer in the frame of the fluid and the lab observer are concerned, it's the same thing. But however, if the bulk flow is also moving at some v, then as far as the lab observer is concerned, the small disturbances are not simply propagating at the speed of sound, they can be propagating the speed of sound plus the speed of the background or minus, depending upon which direction the bulk flow is moving. And this leads us to the other important point. As you can see, in which case the speed at which small disturbances propagate can indeed exceed the speed of sound. This is possible. Okay. And so this is something to be kept in mind very firmly. And so as we emphasized the last time, the sound speed is the speed at which physical information propagates. In other words, you can learn about me being here via the sound that I am emitting at the speed of sound, right? You cannot tell that I am present here and I am talking before the sound waves that I emit reach you, right? So, and it happens only at one characteristic speed, of course, and because you cannot tell that I am here and I am speaking before the sound waves reach you, the speed of sound is thus linked to the concept of physical causality. And in that respect, it is like the speed of sound, light. The speed of sound is somewhat like the speed of light, but there are important differences. Objects and flow speeds can exceed the speed of sound. There is nothing sacrosanct about the speed of sound. You can have flow speeds that are larger than the speed of sound. Okay, so that's not true. That's not so for the speed of light. Of course, nothing can ever exceed the speed of light. However, the dynamics will be very different depending upon whether the speeds, these flow speeds are lower than the speed of sound, in which case they are called subsonic, or whether they are higher than the speed of sound, and in which case such flows are called supersonic. Right. So now let us go back to the Navier-Stokes equation, and we've already done this. We've already encountered the Mach number. No harm in a little bit of repetition, because now we're talking about the speed of sound, and this is a very important topic. So let's go back to the Navier-Stokes equation for a minute. And so this is what it was. This is of course the Navier-Stokes equation written right. So so never mind this. Yeah. So this is the Navier-Stokes equation written in a Lagrangian frame, and you can immediately tell by the fact that these d's are the straight d's and not the partial d's, right. And so this is your ma, if you will, and these are the forces. There's a force due to gravity, that's a force due to pressure gradients, and this is the force due to viscous terms, right. So now the first term, as we've already seen this, the first term is of order u over t, where u is some kind of background speed and t is some kind of time scale, macroscopic time scale, and that can also be written as u squared over L, where L is some kind of representative macroscopic length scale, right. And we are now concerned with the comparison. Mach number is concerned with the comparison between the first term and the third term, right. So this is the inertial term and this is the pressure gradient term, and so the third term, this term, is of order 1 over rho gradient p. The gradient is as good as 1 over L, right, because why is that? The gradient is something like d over dx, right. So it's something like 1 over L, right. The x we replace by a length scale, right. So we keep the pressure and everything as it is, so the gradient gets replaced by 1 over L, and so you have p over rho, and although strictly speaking c sub s squared is really dp over d rho, we just roughly speaking we simply write p over rho is cs squared, right. So the third term is of order 1 over L cs squared. Yeah. So you want to compare this term with this term. You want to compare the inertial term with the pressure gradient term, and the ratio of the inertial term to the pressure gradient term, as we have seen before, gives us the dimensionless Mach number, which is well, actually the ratio of the inertial term to the pressure gradient term is a square of the Mach number. Okay, where the Mach number is defined as the ratio of the flow speed to the sound speed, and this can be m can be less than 1 or greater than 1. If it's less than 1, such flows are called subsonic. If it's greater than 1, such flows are called supersonic, and the characters of these flows are very, very different. So although the speed of sound is the speed at which information propagates, we will elaborate on this. There's nothing preventing the flow or an object in the flow from traveling faster than the speed of sound. So the thing about subsonic flows being ones for which the Mach number is less than 1, right? Subsonic flows are quasi-hydrostatic. We will see why in a minute. Yeah? You've already seen it actually. Subsonic flows are quasi-hydrostatic. They are influenced mostly by pressure gradients, and the pressure gradients are influenced by boundary conditions, right? So we will go back to this. Why is this so? So now you see, let's go back to this again. You see, the Mach number is essentially the ratio of the inertial term to the pressure gradient term, right? So if the Mach number is less than 1, it means that the pressure gradient term is much more important than the inertial term, right. So, as a result, what will happen is the inertial term is essentially equal to 0, right. So, that is why. So, the equation essentially becomes 0 is approximately equal to G minus 1 over rho of P plus mu over rho V. This is what the Navier-Stokes equation starts looking like, right. So, this is the vector Laplacian. Now, this is not that important for the time being, we can just drop this. Now, if you just take these two terms and set it equal to 0, what does this look like? This is a hydrostatic situation, right. There is no appearance of velocity now, and this is valid for subsonic flows. This is true only for subsonic flows. You can put a 0 here because the inertial term is not so important. That's the whole definition of subsonic flows. So, you look at this and this, it's essentially a hydrostatic equation, right. So, there's no velocity, and so that is why we say that subsonic flows are quasi hydrostatic, and they are influenced mostly by pressure gradients. That's the whole point. Apart from the gravity term, they are mostly influenced by pressure gradients. Pressure gradients play a large part in subsonic flows. Okay, and the pressure gradients are influenced by boundary conditions. What do you mean by pressure gradients? Well, the pressure is larger here and smaller here. In other words, you have to specify how much is the pressure here, how much is the pressure here. You have to specify the boundary conditions. So, that's what this statement means. And all of these are true for subsonic flows where the inertial term is negligible or essentially can be replaced by 0. So, all of these three statements are very, very true for the lower the Mach number, the truer these statements are. If the Mach number is much, much less than 1, say 10 raised to minus 3 or something, these three statements are very true. If the Mach number is something like half or so, these statements are not as true. They are still true, but not as they're not as accurate as what they would have been if the Mach number was 10 raised to minus 3, for instance. Okay, why is that? Because the lower the Mach number, the better the approximation of setting the inertial term equal to 0. That's all, nothing else, right? So, this is what subsonic flows are all about. Subsonic flows. All these three statements are true for subsonic flows, and the more subsonic the flow, the truer these three statements are. Okay, right. On the other hand, supersonic flows for which Mach number is greater than 1 are essentially quasi-ballistic. In other words, they are inertia driven. Again, a no-brainer, right? So, what happens is the third term is not that important in this case. You simply write du dt g. The second term is almost equal to 0, the pressure gradient term, and then you of course have the viscous term, which for the time being we will ignore, right. So, here you used to have the pressure gradient term in the full Navier-Stokes equation, but now for supersonic flows, by definition the inertial term is larger than the pressure gradient term. So, in comparison to the inertial term, I am able to set this third term roughly equal to 0. And then what does this look like? Du dt is equal to g, right. So, this is as good as a bullet. The whole point, the whole distinguishing feature for fluid flows is the appearance of this pressure. Okay. That's the reason the flow of a fluid requires a different treatment from the dynamics. Trying to study the dynamics of a fluid, you need to take the fluid pressure into account. It's in that respect that it's different from the dynamics of a stone or a bullet or something, just something that's ballistic. In this particular case, for supersonic flows, the flows actually, even though they are a fluid, they actually behave more like a stone. They are quasi-ballistic. They are inertia driven. They don't care about pressure gradients, right? The pressure gradient term is equal to 0, approximately equal to 0, and they are not influenced by boundary conditions far away. You see, we simply wrote, that is all there was, right? They don't care about the boundary conditions, far away, especially if you're sitting on the parcel of fluid. The boundary conditions don't really matter that much, and they generally contain discontinuities such as shocks, and this is a very important thing. We will talk about this in a minute. There are some counterintuitive features that arise in supersonic flows, and the situation gets especially complicated when one tries to transition between subsonic and supersonic flows. If a flow is transitioning between the Mach number less than 1 to Mach number greater than 1, you have to pass through what's called the sonic point, where the velocity of the flow becomes equal to the speed of sound, and so one has to be really careful in all. We will come to all these. For the time being, just to remark that supersonic flows generally contain discontinuities such as shocks. Okay, and they have several counterintuitive features as we remarked. Yeah. So now let us go on to a bit of a graphical illustration. As we said a little while ago, the speed of sound is the characteristic speed at which small disturbances propagate with respect to the background fluid. Okay. If the background fluid is moving, or if the source of sound is moving, same thing, right? It doesn't matter. Either the source is moving through the fluid, or the source is stationary and the fluid is moving. It's exactly the same mathematics, right? Let us now adopt, a scenario where the source is moving, is either stationary or moving. Okay. So now our first illustration is pertains to a stationary source of sound waves. In other words, the Mach number, this really should be a script m, is technically equal to 0, right? Because u over cs and u is equal to 0, therefore the Mach number is technically equal to 0. And what these circles indicate are isocontours of pressure or density. For definiteness, let us consider them to be contours of pressure. So the disturbances, and so the source is located at the center, and the pressure disturbances are propagating isotropically outwards, right? And these are the contours of isopressure, right? So the pressure is constant around any one of these contours, and of course is decreasing as you go out. Yeah. So this represents a stationary source of sound waves. Yeah. Now let us set the source in motion. Yeah. And in particular, this is a situation where the Mach number is less than 1 here. Yeah. So what happens is, so the source is moving to the right. Yeah. Now all of this is with regard to the lab observer. The observer is not sitting on the source of sound. The observer is outside, and he or she is observing how the isopressure contours behave now that the source is moving. Yeah. So the source is still there, and the source is moving with a velocity v, and so the distance the source moves is something like vt, right? and the distance which the pressure disturbances move is something like C sub st. Therefore, and the source is right here, right. So that would be the resultant vector, this essentially. This is supposed to be a straight line. So that would be the resultant vector, right. So the point I am trying to make here is that, first of all, there are two things. First of all, unlike the situation for for a stationary source of sound, the contours are now squished. The contours are now distorted. They are squished to the left. That's point number one. But the other more important point is that, but they're still not intersecting. The contours are still nested. They're still within each other, right? But unlike, let's keep the unlike adjective to the next slide. The main point to be noted is that the source is still in causal contact with all the points on the farthest contour. This is the distance which so this would be the resultant of Vt and C sub st. So what this is showing is that the source is in causal contact, is in communication via these small pressure waves, is in communication with all the points here, even on the farthest contour. This is large here and this would be smaller here, of course. Okay, it will be smaller here, so on and so forth, but it's still in communication with all the points. Okay, and this is true as long as this Vt is smaller than C sub st. In other words, the magnitude of Vt is smaller than the magnitude of C sub st. In other words, V is smaller than C sub s. In other words, the Mach number is less than 1, right. This is true as long as this is satisfied. And it's obvious what we are building up to. We are building up to a situation where this need not be true. If the Mach number exceeds 1, what will happen is this Vt, the length of the Vt vector can be larger than the length of the C sub st vector. And what happens then? This is what happens. You see, in this case, the Vt is, in this case, is larger. The length of this vector is larger than the length of this vector. The source is still here and is still moving to the right, except the Mach number, which is defined as V over C sub s. This is now greater than 1. As a consequence, Vt is larger than C sub st, and therefore what happens here is that the source is not able to be in causal contact with, say, this point or that point. Okay. The source can be, so if you draw the resultant, this is Vt and this is C sub st and this would be the resultant. The resultant outlines a tangent like so. So the disturbances, the effects of the disturbances, it's not so much the disturbances, what we can say is that the effects of the disturbances are concentrated in a Mach cone, and observers outside of this cone do not receive any information. More properly, we should say sound related information or sonic information. Okay, so this is what defines a Mach cone. So, and the angle of this cone, the angle, this half angle, let's call it alpha. Alpha is approximately equal to V over C sub s. Okay, I beg your pardon, it should be C sub s over V. Sorry, it should be should always be smaller than 1. And you can verify this for yourself by dropping a perpendicular. So the half angle is something like C sub s over V. Okay? In other words, it's approximately something like the inverse of the Mach number. The larger the Mach number, the more concentrated the cone. Okay? And this is behind the phenomenon of the sonic boom that you might be familiar with. When a supersonic aircraft flies past, you hear a sonic boom, and so it's only observers within this cone who feel, so the aircraft is flying past, and it's only observers outside of this cone cannot say anything about the aircraft. They might be able to see it. Okay, but that's that. I mean, seeing the aircraft is via the speed of light. But as far as hearing the aircraft goes, they won't hear the aircraft. Okay, and so this is essentially this illustrates the basic differences between subsonic and supersonic sources of sound waves. The other peculiar thing one can notice from this is that these are isocontours, right? These are contours of pressure. So all along this contour, the pressure is constant, say P1. All along this contour, the pressure is also constant, say it's P2, right? Now, for supersonic sound waves, you see that these two contours are allowed to intersect. There's an intersection of these two contours here, the intersection of these two other contours here, and so on and so forth. So at this intersection point, what is the pressure? Is it P1 or is it P2? Well, that's a good question, right? I don't know. That's the answer. The contours are intersecting, so I can't tell whether it's P1 or P2. It's indeterminate. And so this illustrates one of the other problems that can arise in supersonic flows. In other words, this is indicative of a mathematical problem. It's indicative of the fact that there can be discontinuities in the physical quantities such as pressure, velocity, density, so on and so forth. Okay, it's indicative of the fact, it's not yet demonstrated, but it's indicative of the fact that there can be discontinuities in these physical variables, and so we will come to that, and these discontinuities are often shocks, but not always. There can also be things called contact discontinuities, and we will come to that in a minute. So that's it for the time being. Thank you.